Hi guys, welcome back to SEM 2 of your Foundation in Science. This is the first lecture. I'm going to do a summary on this, electromagnetic spectrums. Now these are the learning outcomes we're going to cover in this summary. Understand relationship between wavelength frequency and velocity, as well as to perform calculations associated with all these units, and then understand what is emission spectra and able to explain it, able to relate energy level of electrons to the name of series and part of electromagnetic spectrum, able to calculate ionization energy using wavelength data. The first thing we're going to look at, what is that electromagnetic spectrum? So what is that electromagnetic wave? Electromagnetic wave is a combination of magnetic field and electric field which is perpendicular to each other and travel like a wave. So like showing in this diagram, this is the wave structure, but the magnetic field and the electric fields are actually perpendicular to each other and travel in a wave-like structure in a certain directions. Okay, so wavelength can be used to measure electromagnetic radiations. Wavelength is the distance between two wave crests, here and here. All right, and it also can be measured in terms of frequency. Frequency is a complete wave from this point up to this point. So this is considered as one complete wave per unit time. So therefore, wavelength usually measured in a unit of meter or nanometer. Whereas frequency usually measured in per second because it's per unit time, so also we call that hertz. Alright, that's another unit that we can use, another quantity that you can use other than wavelength frequency. For electromagnetic radiations, we can measure them in the form of wave number. Okay, which is 1 over lambda. What is that lambda? Lambda is actually unit for wavelength. Of course, frequency will be V, that will be the symbol, not unit. Wave number will be this. That's a symbol. Alright, so electromagnetic radiation is a combination of magnetic field and electric field travel like a wave, and then in one particular directions. We can actually use wavelength to measure the distance between two wave crests. We can actually measure wave as well, specify them in terms of frequency, and other than frequency, wave number also used to actually measure electromagnetic radiations. So this is the formula that we're going to study here. The relationship between wavelength, frequency, and velocity. C is actually the speed of light or the velocity of light in a vacuum, and then lambda, which is the wavelength, V is the frequency. All right, so that will be the relationship between the three units or three quantities that we're talking about. Next, now what is that electromagnetic spectrums? Now electromagnetic spectrum cover a wide range of wavelength or wide range of radiation. It started from a low energy. Usually low energy are the one with longer wavelength, a shorter frequency, right? So in this case, we started out with a radio, okay, radio wave, followed by microwave, and then when energy increases further, we get infrared. When energy increases further, we get visible, and then up to UV light. This is hazardous to our skin or to human being, and then X-ray followed by gamma ray. So as you can see that the wavelength is actually decreasing. So when wavelength decreases, what happened to the frequency? Frequency will be the other way around because it's inversely proportional. So in this case, the frequency is actually increases. Okay, so this is a span of a continuous spectrums from all the electromagnetic radiations. And yes, visible light is also considered as electromagnetic radiations. And what is that? How do we calculate the energy of electromagnetic radiations? Now, electromagnetic radiations, like I said, it's always a combination of electric and magnetic field. But then, when they start interacting with matters, they tend to transfer the energy from the radiations to the matter. It's be it a TV, be it a tables, whatever. So when a radiations come into contact with a matter, a solid or a liquid, whatever, they tend to transfer energy. But this energy transferred is in the form of bundles or packets. And these bundles and packets are always with definite size and definite amount, which means energy is not transferred in one lump sum. Energy is actually transferred in the form of bundles of packets. So there is a lot of packets with definite amount of energy and with definite size, and these small little packets are actually travel wave-light because they are electromagnetic radiations, right? So they travel as wave-like with all these particles floating around. So sometimes electromagnetic radiations, also known as a stream of particles that travel like a wave. Okay, and these small little packets, also known as photon. Okay, all these small little packets, we call that as photons with definite size and definite amount of energy. And that is how they transfer energy from one place to another through the distributions of the photons. How to calculate energy of electromagnetic radiations? Now we learned that photons will be the one that consists of all the energy, and a lot of photons actually consist of a definite amount of energy. So to calculate the energy carried by a single photon, this is the formula: energy of the packet, which is for one packet, a single photon, and then this is a Planck constant together with the frequency. This is the frequency of that particular radiations. Of course, these formula can be applied for radio wave, microwave, UV, whatever, as long as it is within the electromagnetic spectrums and as long as we know the frequency. Okay, so just make use of this formula, then we can calculate the energy for a single photons. And what about for 1 mole of photons? For 1 mole of photons, as we know in chemistry, 1 mole meaning that we have to include Avogadro constant, and that is why L has been included. And we have 3 different versions of the formula. You can change them according. So this is actually frequency, and frequency also equals to c over lambda based on the equation given just now, right? So therefore you can change it into another version, which is LHC over lambda. This is another formula, or you can change that in terms of wave number. This is wave number, LHC wave number. Now this all depends on whether you are given with the frequency or a wavelength or even a wave number. So you can suit into a different form of the equations. So that's how we calculate the energy for photons as well as 1 mole of photons. Now let's say if I ask you questions here, what if, all right, a microwave, you're heating your food in a microwave machines. The microwave started and then the wave actually interacting with your food. And that's how the microwave transfer energy to your food and heat it up, right? And do we actually consider that as a single photon if I ask you to calculate the energy for that microwave during that period of time? Or it actually consider that as more than a single photon? Now the answer is very simple, because microwave is actually heating up your food. We don't expect it to be a single photon, because they always travel in wave and with bundles and packets, right? Definitely more than 1 photons. And therefore, when I ask you to calculate, when the question asks you to calculate the energy for that particular microwave during a period of time, we always use this formula. So we always include Avogadro constant, in other words. Because in exam, you may ask, when should I include in Avogadro constant and when should I exclude it? As long as they ask you to calculate the energy, we always include Avogadro constant, and your final answer will always be in joule per mole. Or you may convert it into kilojoules per mole. That will be the energy required, unless in the question it specifies that they want to know what is the energy for a single photon. For 1 single photon, then only you exclude the Avogadro constant, and your answer will be in either joules or kilojoules. Okay, either joules or kilojoules. There's no per mole because no Avogadro constant. You get it, right? So this is how we calculate the energy for electromagnetic radiations. Now this is another diagram showing the span of electromagnetic radiations in terms of photons. Like I mentioned, radio wave will be the one with the lowest energy, hence the photon is the one that carry the energy. So radio wave will have the lowest photons energy, Gamma ray will be the one with the higher photon energy. All right, so this is just a simple illustrations. Next, let's move on to this atomic emission spectra. What is that atomic emission spectra? Now, when an element or when gaseous atom, let's say for example, I have a sodium gaseous atom, 1 mole of sodium gaseous atom. Now, 1 mole of sodium gaseous atom is equivalent to 6.02 times 10 to the power of 23 sodium atoms in a gaseous form. Makes sense because 1 mole. So you have 6.02 times 10 to the power of 23 sodium atoms in a gaseous state that randomly move around. And when these gaseous atoms subjected to any energy input, let's say for example electrical sparks, you put in energy, you sparked this gaseous sodium atoms, what happened? The electrons from the sodium atoms, let's say this is sodium, where we learn a simple electron shell, right? So this is sodium atoms, a single sodium atom with a nucleus in it, sorry, and then you have okay, let's change the color for electrons, green, 1 2, right? You have a nucleus and then you have 2 electrons, 1 2 3 4 5 6 7 8, and then you have 1 here, 1 valence electrons, because the electron configuration is 2 8 1, right? Now what happened when all these gaseous atoms actually expose to electrical sparks? Now electrical sparks will provide certain amount of energy, and what happened when these energy actually sparked on a sodium atom? The electron, okay, the electrons from this sodium atoms will absorb the energy. Okay, now each electrons here will have its own energy level before we expose it to external energy input. Right, each electron here will have its own energy value. Let's say for example the 2 electrons A and B here, okay, 2 electrons A and B will be the one with the lowest energy because it is closest to the nucleus, right? And then the next shells will be further away, then we expect them to consist of a higher amount of energy, and the last one, the valence electrons, will be the one with the highest energy. Okay, now what happened now is the electrons from the lowest energy or from the first shell will tend to absorb energy from the electrical spark. And when they absorb energy from the electrical spark, it will be higher than what it has originally. And what happened now is this electron will tend to jump from the first shell, jump from first shell to the second shell. Okay, and when it jumps to the second shell, this process we call that as excitations of electrons. Okay, and when electrons at in its excited state, what happened when these electron energy jump here? It is unstable because they have high energy content, because they absorb extra energy, because they absorb the energy that more than what they usually can handle. So what happened is it is unstable. And what if these electrons actually drop back to its original first shell? So they first promoted up to the second shell, now they drop back to the first shells. When they drop back to the first shell, they will actually release the same amount of energy that been absorbed to the surrounding. When they drop back, they emit this amount of energy to the surrounding. That's what we call emissions of energy, or emissions of radiation. Sorry. Oops, I'm so sorry. Let's continue. I pressed the wrong button. So emissions of energy or radiations with certain amount of energy. You see that? So the promotions of electrons, when you expose it to the energy input from one shell to a higher shell, it will become unstable, and then when they drop back, that's how they emit radiations. It can emit radiation in terms of microwave, radio waves, or even visible lights, or even X-ray, or even a gamma ray. It depends on the energy provided, and it depends on how the electron move, how far the electron actually jump up to the electron shell. Like I said just now, the electron can jump from the first shell to the second shell. What if you provide enough energy, high enough energy? They can jump from the second shell to the third shell to the fourth, or even fifth, the imaginary shell. And why do we call that as imaginary? Because these fourth shell onwards, it seems doesn't exist because I only have 11 electrons. The third shell will be the last one, right? But imaginary, which means if you have an electrons with an energy level same as the fourth shell, yes, it exists. Or if you have an electrons with an energy level same as the fifth shell, yes, it exists. So it depends on how far an electrons actually jump to the higher level of electron shells and how far they drop back to the original state. And that will account for the emissions of the radiations, the energy of the radiations released. So this is how an atom emits certain radiations. All right, and that's what we call atomic emissions. And next, we look at hydrogens. Now, why we chose hydrogen as a standard here to study about the emission? So hydrogen has only one electron, so it makes everything simple because you only have one electrons, and the emissions pattern will be much simpler compared to others. Let's say, for example, if I really put sodium in, you have 11 electrons, and these 11 electrons are actually exposed to the energy, and they can jump around. They can promote to second shell, third shell, fourth shells, and then they can drop back to second shell, drop back to third shells. So that will actually give you a more complicated pattern. All right, let's look at this, then it will be much clearer. Now, emission spectrums of hydrogen. What is that emission spectrum? Just now we were talking about emission radiations, right? Now imagine that this is the discharge tube, and inside the discharge tube you actually fill it up with hydrogen gas. And again, I would definitely not put in one single molecule of hydrogens, right? Usually I'll put in a certain mole of hydrogen gas, because if it is one molecule, that will be too small to measure. So let's say I put in 1 mole of hydrogen gas. So 1 mole, again guys, ask yourself, 1 mole should be equivalent to 6.02 times 10 to the power of 23 molecules of hydrogens. That's a lot, right? So when they're exposed to electrical sparks, the electrical will start from here. Of course, they have different dipole, positive, negative. So the electrical sparks on the gas, okay, on the hydrogen gas. So these hydrogen gas molecules are expected to absorb energy from the electrical sparks. And what happened? Again, hydrogen molecules will have hydrogen atoms bonded together, right? A shared pair of electrons here. And what happens when you're exposed to electrical sparks? That electrical sparks will break the bonds. When they break the bond of hydrogen molecules, you will get 2 separate hydrogen atoms with 1 single electrons on it each, right? The original. See that? You break the bonds. Just now was shared to form hydrogen molecules. Because of electrical sparks, you break the bonds, and now you get a single electrons on its shell. And what happened next? The energy is still sparking on it, right? The electrical sparks are still continue. And what happened to these single electrons? These single electrons will actually absorb energy from the electrical spark, and they try to promote up to the second shell, or even the third shell, or even the fourth shell. It depends on the energy provided. So this electron will jump to the second shell, or even to the third shell. Let's say it jumped to the third shell. This is where they jump. When they jump to the third shell, what happened? It is at its excited states, right? Excitations. And what happened now is they will tend to fall back, because when they're excited state, they are unstable, the electrons are unstable, and they tend to fall back. And when they fall back, let's say they fall back to the same original place, the first shell. From first shell to third shell, now they fall back to the first shells. When they fall back, they will release out the energy absorbed. Let's say when they move up here, they absorb 100 kilojoules. And when they fall back, they will release 100 kilojoules as well. Makes sense, right? Initially, I have 50 kilojoules. I absorb extra 100, right, to the third shell. And then when I fall back to the first shell, means I will just release out the 100 kilojoules. I will just keep the 50 kilojoules, which is originally with myself. Okay, so I will release the 100 kilojoules that have been absorbed just now to the surrounding, and these 100 kilojoules will be in the form of radiation. Like I said, depends on the energy. The 100 kilojoules could be just a microwave, or it could be infrared, or it could be a UV light. Okay, and this emissions, these radiations will actually go through a process here with a narrow with a lens that focus the the radiations through a slit, and then another lens, and then they'll go through a prisms, and this prism will actually separate them. What does that mean by separate them? Aren't we talking about just one radiation? Not really. Just now we were talking about only one electrons, right? Imagine you have another hydrogen atoms here. These electrons from these atoms also promoted up to a higher second shell, third shell, and then they drop back. And then you have this amount of hydrogen. So you have a lot of hydrogen atoms at the same time exposed to the energy, and the electrons actually promoted up to the different energy level. At the same time, they fall back to the original level. So you expect a lot of radiations being released out at the same time. And how can we actually separate them? This is the use of a prism. The prism will actually separate the continuous spectrums, the continuous radiation, all the radiation into a single individual lines. And these lines will appear on the black background. That's how we get the line. See that? So how many lines here? I have 4 lines. 1, 2, 3, 4. I have 4 different types of radiations with different amount of energy. How do I know they have different amount of energy? Because all with different wavelength. Different wavelength meaning that they have different frequency. Different frequency meaning that they have different energy. We can use the formula to calculate E equals to LHV or E equals to LHV to calculate the energy. As long as the wavelength is different or frequency is different, we expect them to have different amount of energy. And now we have 4 lines, which means we have 4 radiations with different amount of energy, and this is how they arrange on the black background. And this whole thing with the black background with a colored line on that, we call that as a line spectrum. So we call it as hydrogen line spectrum because it's resulted from hydrogen atoms. Okay, now, like I said, it's a colored line. That would means the radiation here from 656 nanometers, 400, 400, and 400, all these are actually within the visible region of the electromagnetic spectrums. That's why we can see them as a colored line. They are visible to us. What if they release a radiations or a series of radiations with energy level or with wavelength that is in UV, that is in X-ray? Can we see that as a visible line on the black backgrounds? Never. We will never see it. So how do we identify it? So we have to put them under certain instrument to observe the line, not with unaided eye. Okay, but if it is a visible region, if it is a visible radiations, a colored light, then yes, we don't need a special instrument for that. We can see the color. I have a red line here, I have a green line here, I have a blue line here, I have a violet line here. So that's how we see that. So basically they're trying to say that emission spectrums of hydrogen tends to produce visible light radiations, and these visible light radiations will go through a prisms, and they will actually separate them into individual lines on a black background called a line spectrum. Okay, and what's so important about this line spectrums? Okay, what's so important about these line spectrums? Now look at that. We have the lines, right? And each line will have its own wavelength, 656 nanometers, let's say, for example. Can we use these wavelength, apply into the equations to calculate the energy of these particular radiations? Yes. Right, we can calculate that. So you can actually apply the formula E equals to LHV. And of course, this is given as a wavelength. Then you can change it into E equals to LHC over lambda. And then you substitute the lambda in. This is a constant, which is speed of light. This is a Planck constant as well. And this is also a constant. All three are constant, so the only changes will be the wavelength. And from here, we can calculate the energy. So we got to know the energy here for this line. And later we apply for the same thing for the rest of the line, then we can get the energy value for each of these lines produced. And each of these lines actually representing the energy level of each electron shell. So from there we can study the energy level for each electron shell. Okay, let me repeat it again. Some of you may confuse here. See that? Okay. Let me change it into a simple way. N equals to 1. Okay, wait, just a minute. Okay, let's say, imagine now I have a sodium atoms again, or unknown elements, let's say, unknown elements. Now, n equals to 1 is the first shell. This is nucleus. Okay? N equals to 2, n equals to 3, n equals to 4, first line, second line, third line, fourth line, and then n equals to 5, and then you have the fifth line. Okay, imagine these are the electron shells. N equals to 1 is the first shells that closest to the nucleus, and then we have electrons in it, of course. All right, let's see. I have electrons A here, electrons B here, and then I have another electron C here, random, right? And then I have another electron D here. Okay, just random arrangement. Okay, what happened when this particular atom actually exposed to discharge tube, electrical sparks? They absorb energy, right? Let's focus on electron A. Electron A actually jumped from n equals to 1 to n equals to 3. So electron A they jump from n equals to 1 to n equals to 3. Okay, they jump from there, and then what happened next is electron D jump. When they absorb energy, they jump, they get promoted, they get excited, so they jump from n equals to 1 to n equals to 2. So D jump to the second shell instead, because they different electrons will absorb energy in a different manner. So some absorb more, some absorb less, it depends. We can't actually control that, but then let's see. So electron A jumped from n equals to 1 to n equals to 3. And what happened to A now when they reach at this point? When A actually reach at this point, third shell, is these electrons stable? Never, because they absorb extra energy, which is not supposed to be in. So what happened to these electron A? They tends to drop back, right? So when they drop back to the original positions, when they drop from n equals to 3 to n equals to 1, what happened? They release certain amount of energy. They release radiations, and these radiations will be appeared on the black background with a certain wavelength, which we can actually calculate the energy amount using the formula. Make sense? So let's say from electron A, from the radiation released from electron A, it released out, let's say, 100 kilojoules. Okay, it released out 100 kilojoules. So from n equals to 1 to n equals 3, n equals to 3, drop back to n equals to 1, it released 100 kilojoules. And same thing if we look at D. When D jumped from n equals to 1 to n equals to 2, here, D, and it would drop back, right? So when they drop back to n equals to 1, from n equals to 2 to n equals to 1, when they fall back to the original states, it releases certain amount of radiations again with certain amount of energy, which will appear as a line here, one of the particular line here with certain wavelength. And again, we can use the wavelength value to calculate the energy of this particular wavelength, and we can deduce that the energy drop back from electron D is actually about 50 kilojoules. So now, from n equals to 3 to n equals to 1 is 100 kilojoules. From n equals to 2 to n equals to 1 is 50 kilojoules. Right? So what is the energy difference between n equals to 2 and n equals to 3? What is the energy difference between n equals to 2 and n equals to 3? What's the energy difference here? Can we calculate it based on what we have, based on the existing data? Definitely, right? So from n equals to 1 to 2, the difference in energy is 50. From 1 to 3 is 100. So what is the energy for n2 to 3? Again, 50, the difference. Make sense? I mean, this is just an estimated figures, but that's how we calculate, and that's how we judge the energy level for each electron shell based on the line spectrums. I hope you get what I mean here. So based on each line on the black background, we can calculate the energy for each line here, which represent each radiations, or which represent each transition of electrons. And then from there, we can actually deduce the energy level for each electron shell or the energy difference between each electron shells. Is everybody clear? Hopefully, yes. All right. So this is how we make use of the line spectrums to calculate the energy level or the energy difference between electron shells. All right. Now, next things, look at that. This is some standard. All right. Look at that. Let's look at the first series. These are the series that we actually focusing on. Look at Lyman series. This name. You see that all the electrons actually transit from higher energy level, regardless of 2, 3, 4, 5, 6, 7, or infinity, doesn't matter. But all of them actually transit back or actually fall back to n equals to 1. See that? All the arrow actually pointing back to the same, which is n equals to 1. So whatever transition of electrons from high energy drop to n equals to 1, drop back to the first shell, all the radiation here belongs to Lyman series, and these Lyman series represent ultraviolet region from the electromagnetic spectrums. So whatever radiations released out from a transition of electrons to n equals to 1, it's always within UV light. Okay, next will be if the transitions of electrons actually fall back to n equals to 2 from whichever level here, it can be 3, 4, 5, 6, whatever, as long as they fall back to n equals to 2, then it is considered as Balmer series, and all the radiation here is within visible region. So it's some color lights that we can see: red, violet, orange, blue, green. See that? And if you have electron actually fall back from higher energy level to n equals to 3, then we call it as Paschen. N equals to 4, we call that as bracket, and then we have fun series as well when they drop back to n equals to 5. These three will be categorized as infrared. So whatever radiations due to the transition of electrons up to n equals to 3, 4, or 5, it is always within the infrared region. You see that? So this is another additional information that we can use when we calculate a line spectrum. Let's see, I give you a scenario here. Okay, let's say I've got the line spectrums. Okay, yeah, this is the principal quantum number which indicates the electron shells. Let's say I have a line spectrum here. Okay, line, 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 line. Okay, this is the line spectrums that I got from an unknown atoms or unknown elements, right? These are the lines that I've got. So what happened next is I'll identify the line A, B, C, D, E, and then F. F will be quite thick here. Later I'll explain why is it so. So A, B, C, D, E, F. I've all these lines, and each of these lines will have a specific wavelength, right? So then I can calculate the energy, 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 energy. All this, I can calculate the energy value. And once we know the energy, right? So once we know the energy from this line, then I can tell the energy level for each cell in a way, right? Because they transit. Next thing is, once we calculated the energy and we know that it is actually within a certain series. Let's say, for example, from the energy values or from the wavelength, we know that this is actually from a visible region of the electromagnetic spectrums. Then we can tell the transition of electrons for all this line is actually fall back to n equals to 2. Right? Because since we know the wavelength, since we know the energy, then we can tell these lines are actually fall back to n equals to 2, which is under Balmer series. So that's what you need to know, right? If I give you line spectrums, you need to calculate the energy. You need to know the energy difference between each shells. Let's say, for example, what is the energy difference between n equals to 1 and n equals to 2? You must be able to tell based on the line spectrum given. Next is, based on the lines here, based on the energy, based on the wavelength, you must be able to tell whether this is from Lyman, Balmer, Paschen, bracket, or Fun series. Then you will know the electron actually transit from high energy to a certain level. If it is Balmer series, it will always transit from high to n equals to 2. It will drop from high to low up to n equals to 2, never n equals to 1, because that is belongs to ultraviolets. So this is how we differentiate them in terms of the series. Next, we look at Rayburn equations. Now, these Rayburn equations, what is that for? Look, this Rayburn equation is actually very useful because, okay, let's explain the units here, the quantity here. The first one, this is obviously is a wave number, right? As long as you have a wavelength, you can substitute in and then you can get a wave number. This is actually a Rayburn constant, a constant value. And what is N1 and what is N2? Right? Now, see, when an electron is in excited state, which means they promote up to high energy level, it is unstable. So it jumped down to lower state to gain stability. So when electron jumps from higher energy orbits or electron shell to lower energy orbits or electron shells, energy is emitted in the form of photons. So these equations, we can use it to calculate the wavelength. If I tell you the electrons actually, let's say n equals to 4, n equals to 2. The electron actually dropped from n equals to 4 to n equals to 2. Okay, they drop here. And when they drop, they release certain amount of, certain energy value of radiations. And these radiations will have certain wavelength. And this wavelength, I'm going to sub into this to get the wave number, equals to the Rayburn constant. And then we can actually deduce what is the n value. Or in this case, are actually given you the n value, 4 and 2. Right? So you can actually put it in. So what is N1 and N2 in this case if the electron actually drop from n equals to 4 to n equals to 2? So what is N1? N1 is 4, or N1 is actually 2. N1 is actually 2. N2 is actually where it's actually dropped from, which is 4. So when you put into the equation, it will be 1 over 2 square minus 1 over 4 square. And it makes sense because this will be equivalent to 1 over 4 minus 1 over 16. Right? So if you put the other way around, otherwise you will get the wrong values. Yeah, it shouldn't be that way because it's minus. So it should be a bigger value minus a smaller value then. Otherwise you will get the negative values. And that is how we use these equations. So either they make the n value unknown, giving you the wavelength, or they tell you that the electron actually dropping from 4 to 2. When they drop from 4 to 2, what will be the wavelength of the radiation release? Then you can use this equation to get the wavelength. And that's the function of these Rayburn equations. Is everybody clear? Hopefully yes. If you're not, then please ask so during our tutorial sessions later. Okay? Let me give you another example, right? Just in case. Let me erase all this. All right. And give you another example, guys. Let's say I have a question here. Given that, okay, I have an electrons dropping from n equals to 6 to n equals to 3. Okay, I have an electron drop from n equals to 6 to n equals to 3. First questions. This is under what series? Is it Lyman, Balmer, or Paschen, or whatever? How can you tell? That's the first question. Second questions. What's the energy value? What's the energy release or emit? How can we do that? We need to calculate, right? Energy, then we substitute into the equations. E equals to LHV, or E equals to LHC over lambda. But then we need to know the lambda, which is the wavelength, before we actually can calculate the energy value release when an electrons actually drop from 6 to 3. Okay, let's solve these two together. First question, this is under which series? It drops to n equals to 3, right? When it drops to n equals to 3, then obviously it's under here, and this is actually under Paschen series, which is an infrared radiations with different energy, of course. So this is under Passion series. Solve the first questions. Done. Second questions, how can we know the energy release? Then we make use of these equations, the Rayburn equations. We put in the n value, n1 equals to 3, n2 is 6, right? And apply the constant, then you can get the 1 over lambda. From 1 over lambda, you will get the lambda, which is the wavelength. From the lambda wavelength, you can apply the formula E equals the LHC over lambda. Then you can get the energy value. Second question solved. Simple as that. See that? So you can use this information given to identify the series, like I mentioned just now, and then how to calculate the energy release when they drop from 6 to 3. Then you can make use of Rayburn equations, put in the n value with the constant, and then you can calculate 1 over lambda, and then you inverse it back, you get the lambda value. From the lambda value obtained, you can sub into these equations, then you can get the energy release from these particular transitions. All right, so this is Rayburn equations. Next, this will be the last thing, convergence limit. Now still remember the line spectrums that I drew just now. They always start with a low wavelength on the right hand side, and then slowly the lines, right, it's getting closer to each other. First they are far from each other, and then they're getting closer until you get a continuous band. All right, like that, a continuous band. This continuous band, we call that as a convergence limit. And what is that for? Look at that. At the limit of convergence, they merge into a continuum, like a continuous band, right? Now beyond this point, when the energy value or when the wavelength, they always start with low wavelength here, 600 and 650, and then 400, right? Let's say this is about 300. That's a wavelength. And wavelength, the smaller the wavelength, guys, 600, 400, 400 to 300, that indicates higher energy. Make sense? So when the lines are actually having higher energy, means they are actually further away from the nucleus. The promotion of electron, a transition of electron, is actually from even a higher energy value when they drop back. So maybe n equals to 5, n equals to 6, n equals to 7, it depends, right? So beyond this continuum, beyond this line, this convergence limit, the electron is free from the attractions of the nucleus, which means beyond these 300 nanometers, beyond this wavelength or beyond this energy level, whatever electrons that go beyond this level, the electron is actually free from the nuclear attractions. So these becoming a free electrons. It's the same case as when sodium change into sodium positive gas with a release of a single electron. This is the free electrons. And this free electron is actually go beyond the convergence limit. The energy value is actually far from the convergence limit, therefore they are free from the nucleus attractions. And that is why make use of these convergence limit wavelength. We can sub into the equations again, L equals to LHC over lambda. We can put this 300 into this, and then we can calculate the energy, and this particular energy value is actually the ionization energy for that particular element. So convergence limit, whatever wavelength, frequency, or wave number given for that particular convergence limit, that particular band here, the black color band or red color, whatever, that combine together, this wavelength is very useful because we can use it to calculate the energy, and this energy is equivalent to the ionization energy. That's the use of convergence limit. All right, so I guess that's it for this summary. How long did I record it? About 44 minutes. That's okay, within 1 hour. So hope you get, if you have any questions on this, please feel free to ask during the tutorial. And that's it. I'll see you again next week. Thank you.